Hello, greeting to you all. My name is A.Malik and I am from CSE Department D section and I am here to display my Tech Talk topic on probability and statistics. The topic name is going to be binary hypothesis testing game with training data. Introduction. Folk binary hypothesis testing game with training data. Focus decision making under uncertainty with two competing hypotheses. Use label training data to build optimal decision rules. Applications, security, signal processing, medical diagnosis, in intrusion detection combines elements of statistic, machine learning, and game theory. Problem definition. We observe a data point and must decide between hypothesis H0. Data follows distribution P0. Hypothesis H1. Data follows distribution of P1. Goal. Choose the correct hypothesis while minimizing errors. Training data samples from both P0 and P1 are available. Types of errors. Type 1 error, which is going to be false positive, choosing H1 when H0 is true. Type 2 error, false negative, choosing H0 when H1 is true. Minimizing both errors is crucial but often conflicting. Trade-off between sensitivity and specificity. Decision rules. A decision rule map observed data to either H0 or H1. Threshold-based rules are commonly used. Likelihood ratio approach. Compare likelihood of data under H1 versus H0. Choose H1 if likelihood ratio is above a threshold. Game theoretic perspective. Two players. Detector. Choose decision rule. Adversary or nature. Chooses distribution within allows uncertainty. Objective. Minimax approach. Minimize worst case decision error. Ensures robust performance under uncertainty. Role of training data. Training data provides empirical estimates of distribution, can be used to train classifiers or density estimators. Split data into training, validation, and testing sets. Help tune decision threshold and access performance. Likelihood based methods estimate probability density for both hypotheses, compute likelihood ratio, probability of data under H1 versus H0, decide based on a chosen threshold to minimize risk, works well with sufficient label data. Discriminative methods use classifiers such as logistic regression, SVM, or neural networks models directly predicts which hypothesis is more likely, focuses on decision boundary rather than density estimation, useful when data distribution is complex. Neyman-Pearson framework. Objective: minimize false negative while keeping false positives under a fixed level. Widely used in hypothesis testing scenarios, decision thresholds are tuned to satisfy a maximum type 1 error rate, often used in scientific experiments and quality control. Robustness and adversarial settings. Adversarial testing assumes distribution may shift slightly. Use robust optimization or distributional uncertainty models. Make detector resilient to worst case scenarios. Important for cybersecurity and adversarial ML tasks. Applications: intrusion and fraud detection systems, spam filtering and malware detection, medical diagnosis from patient data, industrial quality control and anomaly detection, financial risk analysis. Data preparation: collect label samples for both hypotheses H0 and H1. Ensure balanced dataset to avoid bias in decisions. Perform pre-processing, normalization, feature selection, noise reduction. Split data into training, validation, and test sets. Use validation data for threshold tuning and error estimating. Evaluation metrics: accuracy, percentage of correct predictions, precision ratio of true positives to predicted positives. Recall: sensitivity ratio of true positives to actual positives. False positive ratio, fraction of negative incorrectly classified. ROC curve, trade-off between sensitivity and specificity. Decision threshold tuning, adjust threshold to control trade-off between type 1 and type 2 errors. Lower threshold increases sensitivity but may raise false positive. Higher threshold reduces false positives but may miss true positives. Choose threshold based on application specific requirements. Use validation data to tune and lock thresholds. Real-time implementations. Deploy trained model or decision rule for live data streams. Optimize for low latency and memory usage. Implement lightweight models for embedded or IoT systems. Continuously update models with new training data. Monitor performance to detect concept drift. Future research direction: incorporation deep learning for complex features extraction, building robust systems against adversarial attacks, active learning to reduce labeling cost. Hybrid approaches combines generative and discriminative models, scaling to high dimensional and streaming data environments. Summary and insights: binary hypothesis testing is a structured decision making framework. Training data is critical for building accurate decision rules. Game Theoretic view ensure robustness under uncertainty. Balances between type 1 and type 2 error is a key. Widely applicable in AI, machine learning, security, and engineering domains. Thank you.